Hey, Chem 1110. Today, we're going to start in Chapter 3.3. Chapter 3.3 will discuss electron configurations and orbital diagrams. Now, to understand about electron configurations and orbital diagrams and what they mean, we need to recognize that what we're going to do is we're going to combine two topics we discussed in earlier lectures. First topic is quantum numbers. Remember, we said that quantum numbers are similar to addresses of electrons, and we have certain rules of allowed sets of quantum numbers, and we're going to be using that in this section to help us learn about a little bit more about electron configurations and orbital diagrams. Another important topic that we're going to include is the structure of the periodic table. What's important about the periodic table is that the arrangement of elements and where they're located at in the periodic table reflects how electrons are located in these atoms. So these are two topics that we're going to begin with today. And in my PowerPoint, I suggest you look at the definitions of what an electron configuration is. We define an electron configuration as a notation to show how electrons are arranged in an atomic orbital. And we're going to, again, sort of show how this is related to the address of the electron. Orbital diagrams give us more information. These are diagrams that are very similar to the electron configuration. However, they include information on the spin of the electron. And again, we're going to use arrows to represent the spin as being up or the spin being down. And we'll get to that topic a little bit as we begin discussing about electron configurations and how we're going to write them. Now, we're going to focus on the electron configuration for atoms in their most stable state. And what we call this the ground state electron configuration. And what we're going to do, our goal in this section is we're going to use the periodic table. We're going to use quantum numbers, and we're going to use energy level diagrams, something a little bit new that we may not have any background in. So we're going to think about ground state electron configuration, and we're going to look at the hydrogen atom. So we're going to start simple, hydrogen atom. And we're going to use an energy level diagram to show how the orbitals would be arranged in the simple hydrogen atom. And again, remember, hydrogen only has a single electron. So an energy level diagram. We have energy on this side. And then we're going to show our energy levels, the principal quantum numbers, and the sublevels that are associated with them. So when we think about hydrogen, this would be n is 1. When n is equal to 1, we only have a single s orbital. When n is equal to 2, we have a 2s, and we have 2p orbitals. When n is equal to 3, we have 3s, 3p. And we would have 3d. So this is what we call an energy level diagram. And we're going to begin with the hydrogen atom. And what we're going to do is we're going to move through the periodic table, and we're going to modify our energy level diagram when we get to situations in which we have more than one electron. And this adding electrons to atoms as we move through the periodic table is known as the Aufbau principle. So let's begin with the hydrogen atom. And what we need to recognize from the hydrogen atom's position in the periodic table, and we would look at hydrogen, and we would recall that the atomic number is 1, and it's a neutral atom. The single hydrogen atom has a single electron since it only has one proton and it's neutral. And the way we describe the electron configuration for hydrogen is using our quantum numbers that we discussed earlier. There's the electron configuration for hydrogen. Again, we can think of it as an address of where an electron might be located at. This one represents the first principal energy level, and this superscripted one tells us that there's a single electron in that particular orbital. Now, this is the electron configuration. We can give more information about how we could represent the electron, and that's in the orbital diagram. The orbital diagram is very similar to what we drew in our energy level diagram here. The orbital diagram oftentimes we might use a box, sometimes we use a single line. Whichever way you prefer is fine. The orbital diagram represents the single orbital. In this case, it has a single electron. And by convention, we usually show it as spin up the first electron. If you show it as spin down, that's fine. It's either spin up or spin down. That's completely acceptable, whichever way you like. But there is only one electron. So that's the hydrogen atom. Pretty simple. Let's move through the periodic table. If you would move through the periodic table, we would get to helium. And this is the essence of the Aufbau principle. We move through the periodic table, we add another electron. Let's start all over again. Here's helium. Helium has a second electron. Again, we add electrons to the lowest energy configuration first, and we're going to put the electrons in the first principal energy level, N is 1, and we're going to call the electron configuration for helium one represents the electrons are in the first principal energy level, and this superscript tells us there's 2. Notice I didn't write anything in there because we have to think carefully as to how we put electrons in that particular orbital. And let's write the orbital diagram for helium. And we need to use a rule to write an orbital diagram for this situation. So this is the orbital diagram for helium. We have a box. And now we have to think about how electrons are arranged in an orbital. Each orbital can only have 2 electrons. And each electron needs to have a unique set of 4 quantum numbers. And in this case, the spin quantum number for the 2 electrons have to be different. So if we think of helium, and this is helium's orbital diagram, one of the electrons have to have a positive 1/2 spin number. The other one has a negative 1/2, and it has spin down. Now let's think about helium and show, using a convention, as to why this follows what we call the Pauli exclusion principle. The Pauli exclusion principle simply states that 2 electrons within an orbital have to have 4 unique quantum numbers, and their spins are going to be opposed. So this is the Pauli exclusion principle. Very important. Important enough that we're going to write it up here so everyone has a copy of this, and don't forget it. Pauli exclusion principle. So what it tells us, I think this has to be LE, Pauli exclusion principle. So what this tells us is that each electron has a unique set of 4 quantum numbers. So let's look at the two electrons in the helium orbital diagram. And let's look at this one first. One way we sometimes write these is using a notation in which the first number represents N, the second one L, the third one our magnetic quantum number, and the fourth one the spin quantum number. And we're going to show this for both electrons, for this electron and for the other electron. So this is the electron that's spin up. I'll just put this here. And then we'll show the same notation for the electron in that orbital diagram that has spin down. So both of them are in the first principal energy level. They both have an N value of 1. The only allowed value of L is 0. Likewise, the only allowed value of our magnetic quantum number is 0. So up to now, they both have the same 3 quantum numbers. So they have to have something unique about them. One of them is spin up, and that's positive 1/2. And the other one is spin down. That's negative 1/2. So we end up with 4 different quantum numbers. Well, a unique set of 4 quantum numbers. The first 3 quantum numbers are identical. It's this 4th quantum number, the spin quantum number, that gives us a unique set of a different 4 quantum numbers for each individual electron. Very important. Now, besides the Pauli exclusion principle, there is evidence for why electrons have opposing spins, and it's due to stability. If we think of these as having electric spins, one upward and one downward, an electrical charge that's spinning generates a magnetic field. If these were both pointing upward in the same direction, they would have a magnetic field that repel one another. When one spin is up and one spin is down, well, what happens is we get an attractive situation for the magnetic fields. In this situation, when we have an electron up and electron down, what we say is the spins are paired. And that's the situation we get for helium. The spins are paired. In other words, both spins are in the same direction. And that's the Pauli exclusion principle, a very important fundamental for helping us understand a little bit about how electrons are located in atoms. And we're going to move through the periodic table in our next lecture and go through the complete first 2 periods, and we're going to introduce some more rules. But up to now, this is a little bit about the electron configuration and the orbital diagram for the first 2 atoms that we know, that's hydrogen and helium. More on the topic in our next lecture as we move through the periodic table, and this will be continued on Friday. Thanks.